So let's introduce conditionals, which are if-then statements. Here's our definition. So let P and Q be statements. If P, then Q is a new statement. It's denoted with P, an arrow, and then a Q. This is also pronounced P implies Q. Or if P then Q, and these are conditionals. This is the statement with the following truth table. So I'm going to show you explicitly the truth table for this statement. P implies Q, or if P, then Q. Okay, so I have P, Q, and P implies Q. So P could be true or false. Q can be true or false. And so the first two columns of my truth table, I list all possible options for the combinations of P and Q. So the definition of P implies Q and the definition of what you get when you see if P then Q is this truth table. It must be true, false, true, true. Okay, let's see some examples. So I'm going to write some conditional statements down in the form if P then Q, and then we'll decide whether or not they're true or false. So here's my first one. If 7 is odd, then 7 squared is odd. This is a conditional. It's an if-then statement. This here is my P, and this here is my Q. Now, P happens to be true. 7 is an odd number. Q happens to be true. 7 squared is an odd number. So I'm in the first row of my table, true, true. And if I have true and true for P and Q, I have P implies Q is true. That's a true statement. So I could say, if the function f of x, being the absolute value of x, is continuous, using the calculus idea of being a continuous function, then f of x, which is the absolute value of x, is differentiable. This is an if-then conditional statement. The first P statement happens to be true. So this is a true statement in calculus. And this second statement, you might remember, happens to be false. So I'm in the true-false row of the table, and by definition, the output is false. So this is false. Let's do a couple more. So if you are 10 feet tall, then birds exist. So I haven't met you, but I'm guessing that you're not 10 feet tall. So this statement is false, and birds do exist. I've seen one before, really. So I'm in the row false, true. By definition, the if-then statement happens to be true. And let's do one more where we're in the bottom row. So if a circle has a corner, then You owe me $10. Okay, this is a true statement. It's definitely true because a circle does not have a corner. A circle's round. There's no corners. So this first statement is false, meaning no matter what I say after that, it's true. It's true. The whole if-then statement is true. So that's sometimes a catchy point for some students. If you look at this truth table, if the P statement is false, it doesn't matter what the Q statement is. The result is always true. Because of that, watch what I'm going to do now. I'm going to say if n in n is odd, then 2n plus 1 is even. Now, this first phrase here is not a statement because I don't know the value of n. N could be 1, in which case this would be true, or n could be 2, in which case this is false. But that doesn't matter if I'm dealing with an if-then statement, because if the beginning P is false, the result is always true. So if I'm trying to decide if this conditional is true or not, I might as well just assume that the hypothesis, the beginning statement, is true already. Because if it's not true, then I have nothing to worry about. So we can assume this is true in order to continue. So I'm going to assume I have an odd number, and if I do have an odd natural number, then yes, it is true, it is true that 2n plus 1 is even. So under the condition, that's why conditionals, under the condition that this is true, it does follow that 2n plus 1 is even. So this entire statement is true. Let's do one more just like that. So how about if x is a real number but not a rational number, then x is an integer. So again, this here is an open statement. It depends on what x is. But because we're doing a conditional, I don't have to worry about the situation when it's false. Therefore, I assume that this is true. So I can assume I have a real number that's not a rational number. It's not true that that condition implies I have an integer. This is false. This is because pi is a possible candidate for x. So pi is a real number that's not a fraction. And pi is not in Z. So this is a false statement. So conditionals are very important for you to understand. You need to make sure you fully understand what we're talking about here. Read the text. There's also a section in the text where they discuss different English phrases that are equivalent to saying if P then Q. So for example, you could say Q whenever P. So you could say Q whenever P. And that's an English equivalent statement to if then. Or another equivalent statement could be P is a sufficient condition for Q. The reason why there's a bunch of different English phrases that all mean if P then Q is because this concept is all over the place in mathematics. In fact, most theorem statements will be of the form if P then Q. Okay, so practice with this and make sure you got it. I'll see you for the next video.